Everyone, I have prepared this video um, to introduce the audience uh, to a completely new perspective on vectors. You have seen vectors throughout your life, um, but this perspective is totally new. And why should you bother about this? So you should watch this video if you want to apply vectors to polynomials, to periodic signals, even to documents, attributes in machine learning, and images. And even more, vectors, this new perspective allows you to give a geometric meaning to complex numbers. Complex numbers are much more than this square root of -1 thing, which many people they use, and when you ask them what this means, they say, okay, the meaning doesn't matter. The meaning doesn't matter. If you don't know the meaning, that's your problem. So let me remind you how you were taught a vector. So typically in these textbooks on linear algebra, the introduction of a vector is given as a list of numbers. So this list has 4 elements: 2, 0, -2/3, and pi. Notice this comma, yeah? Because of this comma, this is called a list representation. Alternatives also exist where you just write them as a row vector. So this is a row vector and this is a column vector. Yeah, and because it's not very easy to write this in a document, when many people, when they write this list, what they mean by this is a column vector, because column is very common compared to row. Now this view was just to get you started. This is very easy to actually understand, but this is not very useful. If you see a vector as a list of numbers, I'm afraid it will not help you other than number crunching. So this new perspective is the function view. So this same vector which we saw there, remember these 4 elements, yeah? 2, 0, -2/3, pi. You can think of these numbers as if they were assigned by some function. So I listed those numbers. So this 2 can be assigned to 0. So this is the index, yeah, the 0th element, the first element. So that was the second element. Actually, this is the first element. And that -2/3 assigned to the index 2 and pi assigned to the index 3. Here, because we do not have any context, so we just choose these simple indices without any meaning. But this function view opens a whole new world of applications you will see now. Because in problems we will have a context, and then we will know what we mean by these zeros and ones and twos and threes. So let me start with polynomials. So let me write that vector again for you so that you know I don't have to scroll back and forth. It was 2, the list was 2, 0, minus 2/3, and pi. Now consider a degree 3, actually it's not 4, it's 3. A degree 3 polynomial, the highest exponent is 3. If you can observe, there is a very clear correspondence between this polynomial. So if you consider a function from the exponents, yeah, this is an exponent, this is an exponent, to coefficients, yeah. So this pi is the coefficient corresponding to the exponent 3. This minus 2/3 is the coefficient corresponding to the exponent 2. Exponent 1 has no coefficient, actually 0 coefficient, doesn't appear. And 2 corresponds to x to 0th. So suddenly, this also means that a polynomial can be specified uniquely by a vector. So this was the advantage of viewing this as a function. And in fact, any degree n polynomial of this form can be specified by a vector. Yeah? I just list the coefficients and I see each coefficient as if it has been assigned to these exponents, yeah, by some function. I imagine a function f, yeah, which maps these exponents to coefficients, and that is why I can see the polynomial as a vector. Now you might wonder, what do we achieve with this? The manipulation of polynomials by a computer becomes very simple when you store it as a list of numbers. Because if you have two lists, if I have another list of the same dimensions, I add them, I can get a new list. So that will correspond to the addition of two polynomials. Similarly, there are many other operations which are not only simplified, but you have a clear picture as well. So let's move on. Let's say I have a document. Now, of course, a document is a very complex object, but frequently in document analysis, a widely used model is called a word bag model. So instead of caring about all the details in the syntax and the grammar, you just look at each word and see how many times has it appeared in the document, this frequency. Yeah. So this word bag or bag of word model just looks at any word, yeah, and it maps it to its frequency. Yeah. So let's see an example. Let's say I have a document and which only contains this text and nothing else. Yeah. So we will ignore the plus and the colon because every function assumes a domain. So let's say our domain in this bag of words model is the alphabet, English alphabet. The English words. You can imagine all possible English words, all valid, yeah, valid English words. So we just, what will this function do, this bag of word model? It starts at linear. Yeah? Now if you look at the document, this is all the text. Linear appears only once, so linear is mapped to 1. Algebra appears twice, here and there, so algebra appears twice. Geometry appears once. And that's it, we have a model. Now of course, the domain of the function is all the English words. So how about the other words? All the other words don't appear in these documents. They are mapped to 0. So any other word not appearing in this document is mapped to 0. This is part of the definition of the word bag model. So you cannot say that this is a vector with 3 elements. Yeah? This is a vector with a very large number of elements. Most of them are 0, and actually there is a name for such vectors, sparse vector, which has lots and lots of zeros, yeah? And only 3 non-zero elements. Now computers can be used to actually store these vectors, because you don't need to store these zeros. So there is a very clever representation of such sparse vectors, and that is called a dictionary. Yeah? So instead of representing this as a vector with just 3 zeros, with just 3 non-zeros, yeah, this 1, 2, and 1, and lots of zeros, we simply list in a dictionary. We simply mention the non-zero elements. Yeah? So linear appears once, algebra appears twice, geometry appears once, and we just close this. And anything not appearing, so the definition of a dictionary is that any element of the domain, and here the domain is all the English words, not written in the dictionary is understood to map to 0. So that 0 is actually implicit. Yeah, you don't need to. So the problem with this traditional listing of elements of a vector is that you have to write those zeros as well. You cannot eliminate it. Another example is in machine learning, and that is attributes. Yeah. So imagine you have some data set. In data set, each item will be represented by a collection of attributes. So an attribute will have a name, and it will have a value. So as an example, a consumer can be seen as an item, yeah, or as an example. That consumer could be represented by his age, yeah, one attribute, education level, years of education, the second attribute, and the income, yearly income, the third attribute. So a particular consumer, let's say consumer so and so, will be represented by a vector, and because these are the only 3 attributes which are non-zero, so you can imagine a function or from the list of all possible attributes in a particular domain or particular context, and these 3 attributes, age maps to 30, education level maps to 16, and income maps to 45,000 probably dollars per annum, and this is a function, and this is also a vector, because we know this is a sparse vector, lots and lots of zeros. So we have a particular consumer, let's say consumer number 1 is represented by a vector. Now, how cool is that? Now let's move on. This is even more interesting. So here I have actually it's a more elaborate example of this attribute value thing. So let's say we have products and resources. So let's say there is a factory which makes things using 5 resources. So it uses metal, it uses concrete, it uses plastic, it uses water, and it uses electricity. How many resources? 1, 2, 3, 4, 5. Now use uppercase D for the set of resources. Now the factory has the ability to make 5 different products. You see this thing, these are different products. Now each product will require different resources. It is not necessary that all the resources are actually used in, for example, this product. So if you look into the details of that factory, you can list the type of product. So for example, garden gnome, I think it's this one. So this doesn't use any metal, so that is 0. It does use some concrete, 1.3 in some units, and it uses plastics in that amount, water in that amount, electricity in that amount. So I can, now this is actually an item, a product. Now I can define a vector. Actually it's a function now. Here is a function where metal is mapped to 0, concrete is mapped to 1.3, plastic is mapped to 0.2, water is mapped to 0.8, electricity is mapped to 0.4. So that function represents this item or this product. So that in fact is a vector for me, because this resources are implicit in the context. So I will simply write this as a vector. So the first product is a vector, the second product is another vector, and so on. Now you must have used probability distributions. Probability distribution is also a function where you have some random variable x, and that random variable so this representation of functions by vectors works when you have a finite discrete distribution. So let's say we have a finite set of values x1, x2 up to xn, and each value has an associated probability. Let's say p1, p2, pn. So you can usually you will write something like this, that x1 is mapped to p1, x2 is mapped to p2, so on, and xn is mapped to pn. This is your probability distribution. It tells you how the total probability is distributed among these values. So here we have represented that as a dictionary, as a function, and we can therefore view this as a vector. So if you somehow come across random processes, a random process can, once you understand that a distribution is a vector, so imagine you have time, you can have space as well, but let's focus on time, and these are different time points. At each time point you will have a distribution. At the next time point that distribution could change. So these values don't change, but the probabilities change. So you have a different distribution. So when distribution changes over time or over space, you call it a random process. So imagine a random process can be seen as a sequence of vectors. Now how cool is that? Now even images can be represented as vectors. So for simplicity, we go for a black and white image, because for different colors you will use different vectors. So let's say I have a black and white image, 1025 by 768 pixels. So these pixel coordinate pairs can be seen as, this is the interval from 0 to 1023, and this is the interval from 0 to 768. 7, and this notation will also include the real numbers. So you take the intersection with the integers. So imagine you have a two-dimensional plane. Yeah? So if this is 0 and if this is 1, 0, 2, 3, so all the points between these two, and similarly this is 767. So just this cross will have all the points, integers as well as non-integers. So if I take the intersection with integers, I just have the pairs of integers. Those will be used as indices, and imagine a function which maps these index pairs to real values, and those real values are basically intensities. Yeah. So a black and white image can only have intensities. The red, green, blue channels, for them you can use 3 different vectors. So now this is an example. Let's say 0 represents dark or black, and let's say 255 represents white, which is typically the case in grayscale. So this is a typical image. Yeah? So 0, 0, so the pixel coordinate pair 0, 0 maps to 0, black. 1, 0 maps to 32, some grayscale, and so on. So this is a dictionary, and this is hence a vector. Yeah. So this is a vector because this 2D nature comes from pixel. It doesn't come from intensities. You still have a vector of intensities. Yeah? So because the function is from a pair of pixels, let's say ij, to a real value, intensity. Let's say I is the intensity, I of ij. Yeah? So these intensities are real numbers, and when you combine them into a vector, you have a vector. So an image is a vector, whether you like it or not. So let's move on to the next topics, and that is the sinusoids. So let's consider a sum of a finite number of cosines. So if you look at these cosines, there is a fundamental argument, theta, and all the next polynomials, sorry, not polynomials, the cosines, they are just integer multiples. So if this is theta, this is twice theta, thrice theta, and so this is n theta. And these, then they are combined by some coefficients. And you include this a0 because cosine 0 times theta is cosine 0, and cosine 0 is 1. So that's why you have to include this. Now this can be specified by the vector of coefficients. Yeah. So you can imagine that these numbers, like this 2, you can imagine a function where this 2 maps to this a2, this 1 maps to a1, that 0 maps to a0, and this n maps to an. So you can see this sum of cosines as a mapping from integer multiples of the argument, the fundamental argument, to coefficients, and hence this sinusoid, sorry, this sum of sinusoids can be specified by a single vector. It's very simple. Now such sums of sinusoids can be used to represent a wide range of even functions, even periodic function. Why? Because these cosines are periodic. So a sum of such periodic functions will be a periodic function. And even because a cosine is an even function. Yeah? If you look at cosine, it's an even function. Yeah? The value on this side and the value on this side near 0, they are the same. So if you add even functions, this function will also be even. So sometimes we also need odd functions, and for that you can think about a sum of sines in a similar fashion. Just a's are replaced with b's, and there is no 0 here because sine of 0 is 0. So this such a sum of sines can be represented by this vector. Now a sine, if you look at its plot, it goes like this. So a sine is an odd function because the value on this side and the value on this side, they have opposite signs. One is plus, the other is minus. The values are the same otherwise, the numerical values, except for the sign. So a wide range of periodic functions can be represented by these sums of sines. Sometimes we need periodic functions that are more general. Any periodic function, not just any, but at least those representable by n sinusoids. So if I take sum of sinusoids where I combine the even sinusoids as well as the odd sinusoids up to n, and I can choose n to be large enough to represent a wide range of periodic functions. If I need to represent a wide range of periodic functions, I have to choose n to be large enough. Now, you can also write this in, this is said to be in a rectangular form because if you have seen rotating vectors, yeah? So a point rotating in a circle has actually two projections, one on the x-axis, one on the y-axis, and this forms a rectangle. So it's a rectangular form. You can also turn it into a polar form by combining these combinations of sines and cosines and some trigonometry, and you can use this. Yeah? So A1 and B1 are collapsed to a single magnitude and a single angle. So you can move between rectangular and polar forms by these formulas. If you want to move from rectangular to polar, you use this formula. Yeah? A and B are combined to give C, and A and B are combined to give the angle. And if you want to go from polar to rectangular, you use this form. This is nothing actually new, so you already know that. But we have a problem. If we want to represent things by vectors, it is easy for sum of cosines, very straightforward. It is easy for sum of sines, that is also very straightforward. But if I want to represent this general sum of sinusoids, which has in the rectangular form actually pairs of coefficients, and it will be very difficult to represent this by a vector, because if I list this as a list of coefficients, then I have to somehow remember that, oh, alternate, so it's not very convenient. Yeah. So if you look at this, we can spot a pair of coefficients A1, B1, and we can also spot a pair of sinusoids. So cosine theta, sine theta. Now these we can imagine as if these two pairs have been multiplied. Of course, you have to give meaning to that, but it would be nice to have some mathematical machinery which allows us to write pairs of coefficients, pairs of sinusoids, and then multiply them. This is multiplication. Now, but this is not straightforward. This must remind you of complex numbers, and you can somehow believe in the math textbooks, and they can tell you how to multiply complex numbers, but they don't motivate, and they don't even give any meaning. So I don't want to explain these complex numbers by this nonsensical way. I mean, if I use this as a means to introduce complex numbers, this, of course, this has a meaning, a very deep meaning. It's not very easy to introduce it to newbies. So let me use this simple idea of pairs of sinusoids and a pair of coefficients to introduce complex numbers. So complex numbers will be understood from properties of sinusoids. So let's get into, because we have pairs, so imagine I have a plane, a Cartesian plane, where I have x-axis, y-axis, and I can have a point xy. So x comma y. So because you have been used to Cartesian plane and vectors, you typically imagine this to be the tip of a vector from the origin. So you see this as a vector. And similarly, you can have another point, another vector, and you can add, and you see things like that. So so one way of looking at this point is as a tip of a vector, but you can also forget about the vector and you just see this as a point in its own right. And let's say this is your mathematical object. You want to call this z, and you want to manipulate these different objects, which are pairs. So when you and in that sense, it's called a complex number. Yeah. So this will be a complex plane if you just see the point. And if you want to take those vectors with their coordinates, so if I use the vector, I will have coordinates, x coordinate, x component, y component, x coordinate, y coordinate. Coordinates and components are used in a Cartesian plane of vectors, but we want to forget about those vectors. We just want to see this point as an object, and we want to work with these points. So then we speak of a complex plane. So this is not a Cartesian plane because it will have properties slightly different from that. And these values on the x and y axis, so this is x and this is y, and that's why you have that pair. This will not be called the coordinate. Yeah, this will be called the real part of x, and y will be called the imaginary part of x, xy. Now it's not imaginary, actually they are both real, because this is a real line and this is another real line, and this is just a pair of two real numbers. There is nothing imaginary about it. It's very unfortunate that people still call it imaginary, but I can't change their minds. So you will realize in this video that there is nothing imaginary about this y. This y is as real as this axis. So a point xy in a complex plane behaves very much like the tip of the vector xy in the Cartesian plane, with its tail at the origin. You can imagine a vector with its tail at the origin and with its tip at the point x. So we will use these vectors to motivate what mathematical operations can we do with complex numbers. Now it's very easy because you know how to add vectors. So if you have these two vectors, you just use the parallelogram law, and this is your new vector. So imagine if this is x1, y1, and if this is x2, y2. Now I am using pairs, complex numbers. This will be the sum of these two. So if this is z1 and if this is z2, let's say two complex number, this will be z1 plus z2. So it will be x1 plus x2 comma x2 y1 y2 y1 plus y2. And in vectors you also know something which is called this, so that is actually the addition. We also use scalar multiplication with vectors. If you have a vector of some length and if you multiply it by some number, let's say k, 2 times or 3 times, the length changes. Yeah, the orientation doesn't change. Another terminology is important. When we see this as the tip of a vector, the length of this vector is usually called the magnitude, and this measure of angle is the measure of angle. It's the inclination or orientation of that vector. For complex numbers, we have different terminology. This magnitude will be called the modulus of a complex number. So you don't say magnitude of a complex number, you say modulus. And this angle is attached to a vector, but for a complex number, we will use a different name. It will be called an argument. So this is just to make sure that you have Cartesian plane, complex plane, two different planes. In Cartesian plane, you have vectors with their magnitudes and orientations, angles with their coordinates, x coordinate, y coordinates. In complex plane, you have points, complex numbers. You have each complex number has a real part and an imaginary part, and then each complex number has a modulus, yeah, which is the length of the vector associated with it, and the argument. So the language is actually different. Now, 0 is special because this point 0, 0 is such that any point or any complex number, let's say x comma y, can be seen as if I have added something to 0. Yeah. So any complex number is 0 plus the same complex number. So 0 is actually the additive identity. Now, scalar multiplication, by scalar multiplication we mean the operation where because when you don't change the argument, you have to multiply the same number. Let's say if k is the scalar, that k has to multiply x as well as y. So you have to multiply both the real part and the imaginary part by the same number, and that is what you mean by k times z, a scalar times a complex number. Now, so far there is nothing unusual about the complex plane because everything we are doing is much similar to what we do in a Cartesian plane of vectors. But here is the reason why complex plane is actually something new, and it's the complex multiplication. This is something which is not available in vectors. For example, you can't multiply two vectors. So if I have a vector, if this point is the tip of one vector, and if this point is the tip of another vector, let's say this is v1 and this is v2, I cannot multiply v1 and v2. Of course, I can take the dot product, but that will give me a scalar. That will not give me a vector. And if I go for a cross product, v1 cross v2, I cannot remain in this plane. v1 cross 2, v1 cross v2 will actually take me out of this plane. None of this is desirable. I need to remain in the complex plane. I need to multiply two complex numbers, 2 points, and that is something not available in vectors. So how do I achieve that? And that will actually make you realize why complex numbers. Actually, if this were not true, if multiplication of complex numbers was not special, we would never need complex numbers. We could simply use vectors, as you saw. So let's say I have a complex number xy, let's say x1, y1, and this is x1 and this is y1. Why I can do that? I can actually explain it in this figure. So this is the x-axis, this is the y-axis, and I am talking about this point. This point. So this is x1, y1. Now, if you think about this triangle has hypotenuse of length r1. The argument is theta 1, so the angle is theta 1. So r1 cosine theta is this one, r1 cosine theta 1. And this height will be r1 sine theta 1. So that is exactly what was written there. r1 cosine theta 1, r1 sine theta 1. Yeah? So that is my z1. I can even call it for simplicity, I can call this point z1, the first complex number. Now you should look at another point. So you see this 0 was special in the sense that any point can be seen as a translation from this 0. Yeah, after you add something, whenever you add vectors, you translate. So similarly, in complex plane, when you add points, if you add something to this point, you move it to another point. But there is another way of moving around. Yeah? One is through translation. So translation is one way of moving around, which uses addition. You add a complex number to another complex number. You add a vector to another vector and you translate. But we want to find another way of moving around. And that is, imagine this, you need to be very imaginative to see this. Imagine how can I arrive at this point, which is z1. So let me start not from 0, let me start from 1. This 1, 0. Normally you would call it 1, but because it's a 2D plane, a complex plane, it will have a real part 1 and an imaginary part 0. So let's say I start from 1, 0. So I can, of course, if I want to use translation addition, I can use this and I can use that, but that will not be very creative. Instead of going directly from this point to that point, I first take this path along the unit circle. You remember this 1, 0 is on the unit circle. So let's say I just move along this unit circle and I reach this point. Now, in going from here to there, I did not change the modulus. And if I think of it as a vector, I did not change the length of that vector. So you see, in a circle, the radius doesn't change. So first I rotate this point. I can think of it as rotation. So I rotate this point, and when I reach this point, tell me what will be this point. This is 1, 0. Remember, 1, 0, because this angle is 0. Now, this modulus is 1. It is still 1. But the argument has changed. Yeah. So if I now draw a triangle, this real part will be cosine theta 1. The hypotenuse is 1. Yeah. And this imaginary part will be sine theta 1. So this point, so what I have done by this rotation is that if I represent this in my own language, what the rotation has done, let's say I have this 1 0 and I have rotated this point by an angle theta, and that has led me to which point? To a point with real part cosine theta and imaginary part sine theta. Now I want to reach there. So if you look at that point and if you look at this point, they both have the same argument. So which means that in the second phase, I don't need to rotate further. I just need to multiply this by a scalar, because a scalar multiplication will just change the length of the vector, and if I'm talking about a complex number, it will change the modulus. So first I change the argument by rotating it, and now I will be changing its modulus by scaling it. Yeah. So from 1 0 I reached this point, but if I multiply this from that point onward by a scalar r1, remember r1 is the length of this vector or the modulus of that new complex number I'm looking for. If I multiply this point on the unit circle by a scalar r1, yes, I get my z1. Yeah. So that is actually something very new. Previously I said that any point z can be seen as a translation from the origin, a simple translation by addition, but now you can see the same z1 as if you have obtained it not from 0 but from this 1 comma 0, and you followed a two-step process. First you rotated that 1 0 by an angle theta 1, and remember it's the same theta 1 which actually can be associated with z1, and that gave you the correct orientation, and then you needed to fix the modulus. This has a modulus different from 1. This has a modulus 1, so you need to fix this by multiplying that 1 by r1. Let's move on now from this point. Let's say that I start from this new point and I apply those two steps again. This time I rotate this further by a new angle, yeah, without changing the radius. Yeah. So I stay on that radius, on that circle. I reach this point. So can you tell me what will happen to the z1 when it comes here? So that z1 is basically this, which I got from the previous step. And now if I move it along the circle of radius r1 so that the magnitude doesn't change or the modulus doesn't change, I rotate it by theta 2. So what will happen to this? Look at this. r1 will not change, only theta 1 will change. Theta 1 will change to theta 1 plus theta 2 because the angle is increasing. You see this angle, this is theta 1, this is theta 2, and if you measure it from the x-axis, it will be theta 1 plus theta 2. Yeah. And the same goes for the imaginary part. So from that point onward, because the magnitude is still r1, so maybe you want to reach another point, let's say z, and that point has a different magnitude, different modulus, so you will multiply this r1 by some r2. So now what you have done is basically this. What you have done is you actually reached a new point, and look carefully at the properties. This new point has its angle, which is a sum of two angles, yeah, sum of two angles, and the modulus of this new point is the modulus of one complex number and the modulus of another complex number. So now remember, in real numbers there was something special about 0 for addition, that you add anything to 0 and you get that thing, and there was something special about 1, you multiply anything by 1 and you get that same thing. So because we established that rotation from this point 1 followed by scaling can get you any complex number, I can see this as multiplication. So basically, rotation followed by scaling. By scaling I mean scaling multiplication, scalar multiplication. These two operations, one after the other, should give me complex multiplication. Why? Because I established this for 1. 1, 0 is my identity. But to see it more rigorously, here you have established this in a more general setting. You can think of this as if you started with this complex number, which is z1, you see, modulus r1, argument theta 1. And you can imagine a vector as well, yeah? A vector with a tip that has length, the vector has length r1 and orientation theta 1. And then there is another complex number, another point with argument theta 2, and so let's call this z2 and modulus r2. So imagine if I am multiplying these two, so what happens on the right side is something I already obtained. You see, the modulus times the modulus gives you the new modulus, and the angles are added. So actually you have discovered a multiplication rule for complex numbers. In words, the multiplication rule says that whenever you multiply two complex numbers, what will happen? The moduli will multiply, as you saw there, r1 times r2, and the arguments add, theta 1 plus theta 2. Now this is something you cannot do with vectors. So if I call this v1, vector 1, and if I call this v2, I cannot write v1 times v2 is equal to v. No, I can't do that, because vector multiplication in this fashion, yeah, because here we are using rotation and scaling. In vectors there is no possibility for rotation. Now you can rotate a vector to another vector remaining in this Cartesian plane, but for that you will need a matrix. You can't use two vectors for that purpose. Here you don't need a matrix. Yeah? So here you are using two complex numbers. This complex number is a point, this complex number is a point, and this new complex number is also a point. So you multiply 2 points to get a third point. That is very new. You multiply this point by another point, which has actually, I have to actually show you, this diagram doesn't show z2. This diagram shows z1, and this diagram shows the product z1, z2. Now what is z2? z2 is the point which has an argument theta 2. So which means that I have to imagine theta 2, and because the effect of z2 multiplying z1 was an addition of this angle theta 2, so that's why it has angle theta 2, and the effect on the modulus was R2. So this means that this Z2 must have a modulus R2. So this is my Z2. Now I have a point Z1, I have a point Z2, and if I multiply this Z1 by this Z2, I look at this Z2, its modulus and its argument. I will use the argument of this Z2 to change the argument of Z1, and I will use the argument of this Z2 to change I will change the modulus of this Z2 to change the modulus of Z1. Modulus will be changed by scalar multiplication and argument will be changed by addition. Now this was your multiplication rule in polar form. You can now use these relationships, go from polar form to rectangular form, polar form to rectangular form, use some trigonometric identities you already know, plug it, and you can get your multiplication rule for complex numbers and rectangular coordinates. Now this is something which you studied in your college, but this required you to use that -1 square rooted, which you call I or J. I have never used that. I used pure trigonometry and sinusoids to arrive at these results. Now let's get back to our original question. Why did we start this discussion? Remember, we had a sum of sinusoids that had cosine and sine, linear combinations of cosine and sine, similarly, and so on, and this a0. And the desire was to be able to consider this pair of coefficients a1, b1, and this pair of sinusoids, actually sines and cosines, cosine theta, sine theta. And we saw if we could multiply these pairs, and at that time we had no idea of how to do that. Now we do have that, because now we know complex numbers. Now we know how to multiply two pairs. Now I need to imagine two pairs. Yeah. So let's say one pair is cosine theta, the other pair is sine theta. If I just go with a1 comma b1, I have a problem, because if I use that rule of multiplication, that rule, this x1 times x1, x2, x1 times x2, y1 times y2, but there is a minus sign. If I do this, I will have a minus sign. In this original sum, I don't have a minus sign, I have a plus sign, which means that one of these two will be negative. So I have to use not a1 comma b1, but a1 comma minus b1. So if I multiply a1 minus b1 with my pair of sinusoids, cosine and sine, this is called a complex sinusoid, because it's a complex number, and this is a complex coefficient. So now I can imagine a new sum of complex sinusoids, each multiplied by a complex pair of coefficients. And remember, this can be understood by, because this a0 is multiplying 1, that 1 can be seen as 1 comma 0 in the complex plane. Yeah, that is the multiplicative identity. And this is a0 comma 0, because a0 is real, so anything that is real will have a 0 imaginary part. Now if you multiply these complex coefficients with the complex sinusoids, and then you add everything, you will see a sum that has this sum, this was our original sum, as its real part. So these two are not equal, because you cannot have a complex sum equal to a real sum. But this real sum is the real part of this complex sum. So now we have a simplification where we can go to specify this sum because we know our original sum is simply the real part of this, yeah, and we want to specify this sum because we know these complex sinusoids will be there. Yeah, we don't have to repeat that. So we can now imagine a function which takes me from these multiples. So 1 times theta, 1 maps to a1 comma minus b1. N is the multiple, is actually that is the harmonic number. N times theta, n times theta. So n is mapped to this pair of coefficients, and that one actually 0 times, sorry, it's 0 times theta, because cosine 0 is 1, sine 0 is 0, so it's actually 0 times theta. That 0 times theta is mapped to this coefficient. So which means that I can specify this sum of complex sinusoids as a vector of complex coefficients. So let me go to the beginning and see what was promised. So I promised you there that viewing vectors as functions and not just lists of numbers allows you to deal with many applications, such as polynomials can be seen as a coefficient vector, periodic signals can be seen as a coefficient vector of complex, yeah, coefficients. A document can be seen as a vector, yeah, the bag of words model. So the vector elements of the vector are frequencies of words from the English dictionary, from the English, yeah, words, or from any other language. Attributes, yeah, attribute values, you combine them into a vector. And images can be represented as vectors because the 2D nature comes from pixel coordinates, and the intensities are simply real numbers, so that are just vector elements of a vector. And you used the function view of vectors. This allowed you to give a new meaning, a geometric meaning to the complex numbers. So that was it from my side, and stay tuned because next time maybe I do a similar scanning of matrices. Okay, so stay healthy and stay tuned.